Good afternoon. Welcome to the lecture 4 of hydraulics and hydraulic machinery subject. So this is a revision class for the second year, second semester civil students. So today in this lecture 4, lecture 5, we will discuss about the unit 5 topics, that is the hydraulic turbines. So in this class, we'll discuss purely about the hydraulic turbines, right? Okay. So coming to the syllabus of these hydraulic turbines, you are having the general layout of hydropower installation. So general layout of a hydropower installation. Next one, you are having the layout of hydropower installation, the head and their efficiencies, the efficiencies of hydraulic turbines. There is a mechanical efficiency, a hydraulic efficiency. Like this, you are having some of the efficiencies related to this hydropower installation. Next one is classification of the turbines. How do you classify the turbines? In the unit 6, how do you classify your centrifugal pumps and reciprocating pumps? In the same way, here also we will classify the turbines. Next. So in this classification, we are having, in this classification, we are having the Pelton wheel, the Francis turbine, the Kaplan turbine, the working and their proportions, their velocity diagrams, their working, work done and the efficiency and related problems. So we will discuss all these concepts in this classification of turbines, right? Next, coming to the hydraulic design of a turbine, that is a draft tube, the theory and their efficiencies. Next topic is governing of the turbines. In that, the surge tanks, the unit and the specific quantities. Next one is selection of the turbines, performance characteristics of the turbines, geometric similarities, and the introduction to the cavitation. So these are the topics that we will discuss in this session, right? I think hope it is audible. Yeah. Next, coming to the introduction to the hydraulic turbines. So this topic is already discussed in the class. I think you have written the running notes also. I have drawn a layout of this figure also, right? So in different textbooks or other topics, you can see the layout will be different shape. So ఇక్కడ configuration of log ఉంది మీకు నేను class notes లో చెప్పినట్టు, that is other way. So anything you can draw the figure, right? So here the device which converts, what's the meaning of hydraulic turbine? A device which converts the hydraulic energy into the mechanical energy, right? Conversion of hydraulic energy into mechanical energy or mechanical energy to hydraulic energy is nothing but hydraulic machines. Then the hydraulic machine which converts the hydraulic energy into the mechanical energy is known as turbine. Hydraulic machine ante hydraulic energy into mechanical energy convert cheyadani. Next, from the hydraulic energy into mechanical energy is known as turbine. That converts mechanical energy into the hydraulic energy, that are known as pumps. ఈ పంప్స్ గురించి మనం ఆల్రెడీ డిస్కస్ చేసుకున్నాం యూనిట్ 6 లో. In the unit 5 we are discussing about the hydraulic machines, right? Next, the general layout of any hydroelectric power plant. So this is a head race, this is a bottom layer. For example, if you see the Srisalem power project, right, you are having a dam at the top, you are having a reservoir where you are storing the water at one side. This is a head race under. So this is a reservoir where you are storing. So whenever the gates are open, the water is flowing in this direction. The water is flowing in this direction. Thereby, inside the here the turbine is rotating. Thereby, the high force of water or flushing on these vanes. Thereby, the vanes are rotating of the turbine. Thereby, the electricity is produced from the shaft, right? It is taking into capacitor bank. From the capacitor bank, we are having a pumping the power station. In that power station, we are storing the electricity. Then we are sending the electricity to the other things. So like this, we are having the concepts that are related to the hydroelectric power plant, right? So this is a head race, right? This is a turbine. This is a tail race, the head race, tail race. This is the penstock. This is a penstock. This one is a casing of a turbine. This one is a head. This one is the height of the head race. This one is the total height of the head race, right? So you can draw any type of figure based upon your next. So this is other type of 2D animation. This is other type of 2D animation where you can draw other type of things. So here also you can show the other animated view. So see the head of the water. So this blue color is the head of the water. This is a dam. This is a dam, right? So here the water is at the potential energy. Here the water is a stable condition. So I think the people have come. No. Yes. So the blue color portion is the potential energy where the water is stored behind the reservoir, right? Next. When the water is flowing in this way, it is converted into kinetic energy. So this is a penstock where the water is flowing to the downward stream. Here you are having a turbine. Here you are having a turbine that is mechanical energy. Conversion of this hydraulic energy into the mechanical energy. Because of this tail race, the water is stored at some point and the other ballast water is going down. Here, because of this figure, the turbine. This turbine rotates and generates the current at this point. Then this is connected to the generator room where here the energy is stored and we are sending the energy, that is electric energy, to the other places like industries, villages, towns, etc. So here the electrical energy is generated, right? So this is a general nomenclature of any hydroelectric power plant. So see here, the potential energy is at this position. The kinetic energy is the flowing of the water downwards towards the tail race. The mechanical energy at the turbine. Next one is the electrical energy. So like this, we are having 1, 2, 3, 4 types of energy we are producing in this hydroelectric power plant. That is potential energy, kinetic energy, mechanical energy, and electrical energy. Next. If you get any question, draw the layout of hydroelectric power plant and describe the elements annappudu. You can write all this one. This already you have written in the notes also. Dam ante enti, right? It is a building. So it is constructed across a river or a channel to store the water. The reservoir is also known as head race antam. The pipes of larger diameters are known as penstocks, which carry water under pressure from the reservoir to the turbines. These pipes are usually made of steel or reinforced concrete. The turbines have different types of vanes or buckets or blades mounted on a wheel known as runner. Figure lo chuste you can get an idea. Next, tail race. Tail race, which is a channel carrying water away from the turbine after the water has worked on the turbines. The water surface on the tail race is also referred as tail race. Next, the important terms. See the important terms: HG, net head. These are the important terms that are used in this hydroelectric power plant. What is the gross head? HG. So మీరు figure లో చూస్తే మీకు కనిపిస్తుంది HG and HL. See the HG. This one is a HG. This one is a H. HG is the vertical distance. Hg means it is a vertical distance between the head race and the tail race. Net head is equal to effective head, actual head available in the inlet on the turbine. Therefore, the net head is equal to Hg minus HL, where HL is the total head loss during the transit of the power from the head race to the tail race. Therefore, HF is equals to 4 into F into LV square by 2G D, where F is a coefficient of friction, L is equal to total length of penstock, V is equal to mean velocity, D is equal to diameter, G is equal to acceleration. So these are the terms that we are using for this hydroelectric power plant. Next, coming to the types of efficiencies. We are having 4 types of efficiencies for this thing. The first one is hydraulic efficiency, mechanical efficiency, volumetric efficiency, and overall efficiency. Coming to the centrifugal pumps unit lo kuda manam ilantive chadukunnam. Hydraulic efficiency, mechanical efficiency, volumetric and overall efficiency. Here also the same efficiencies we are seeing here. Okay. Now see the hydraulic efficiency. It is a ratio of power developed by the runner of the turbine to the power supplied to the inlet of the turbine. Since the power is supplied to the hydraulic, the probable loss between the striking jet and the vane rigidly called as a hydraulic efficiency. If the RP of the runner, that is a runner power to the work power is water power, that is hydraulic efficiency is equal to runner power by the water power, runner power by water power. These efficiencies, these are useful for doing the problems. Next, coming to the mechanical efficiency. Mechanical efficiency, it is defined as shaft power divided by runner power. Shaft power divided by the runner power. So definitions are miru. I will provide the separate PDF file of this PPT so that you can read the every unit by seeing this PDF. So if you have any doubts, you can see the video also. Next, coming to the third one is overall efficiency. Overall efficiency is the ratio of power available to the shaft supplied at the inlet of the turbine. As this covers overall problems loss in energy, it is known as overall efficiency. This depends on the hydraulic losses and the slips of the mechanical problems. Now, if you see the overall efficiency, SB by WP, thereby equating the equations 1, 2, and 3, efficiency is equals to mechanical efficiency plus hydraulic efficiency. H is equal to hydraulic efficiency, M is equal to mechanical efficiency. The fourth one is volumetric efficiency. Coming to the volumetric efficiency, the volume of the water striking of the runner of the turbine slightly less than the volume of the supplied of the turbine. So simply we can say the ratio of volume of water actually striking the runner divided by volume of the water supplied to the turbine. That is a volumetric efficiency. Next, coming to the classifications of turbine. నేను మీకు సెకండ్ మిడ్ లో వచ్చే క్వశ్చన్ పేపర్ లో వచ్చే కంటెంట్స్ ఎవ్రీథింగ్ విల్ బి ఫ్రమ్ దిస్ PPTs only, right? The problems కూడా దీనిలోంచి ఇస్తాను. By I think you are having exams on Saturday or Monday, so timetable will come soon. So I will provide the information, right? So these are classified based upon the type of energy, that is inlet, out direction of the flow, head available at the inlet, discharge through the vanes, and the specific speed. This can be arranged like just see here the turbine, name of the turbine and the type. Pelton Wheel turbine, Pelton Wheel, Francis turbine, Kaplan turbine. In that Pelton Wheel you're having impulse type. These two, Francis turbine and Kaplan turbine, are reaction turbines. Then what's the type of energy here? The type of energy is kinetic energy. Here the type of energy is kinetic plus pressure energy. Next, the head. High head Here medium head, here low head. Coming to the discharge, Pelton wheel we are having low discharge. For a Francis turbine you are having a medium discharge. For a Kaplan turbine you are having high discharge. Coming to the direction of the flow, we are having tangential to the runner, radial flow, mixed flow, axial flow. According to the specific speed, low, medium, high. Understood? So if you want to other type of classification, so ఇలా కాకుండా మీకు ఇలా convenient గా ఉంటే so that you can read this type of classification, right? So this is other way of saying the classification, that is according to the type of energy at inlet, impulse turbine and reaction turbine. According to the direction of flow through the runner, tangential flow, radial flow, axial flow, mixed flow. ఇవి కూడా ఇక్కడ ఉన్న టేబుల్ ఫామ్ లో. But if you are have any confusion, if you get a question, you can write this one, right? Next, coming to the inlet of the turbine, high head, medium head, and low head. Coming to the speed of the turbine, you are having low speed, medium speed, and high speed. So this is about the classification of turbines. Next, we'll discuss each type of turbine separately. That is the Pelton wheel theory, the work done, and also the problems related to the Pelton wheel, right? So it is a tangential flow turbine. It is a tangential flow impulse turbine. The water strikes the bucket along the tangent of the runner. The energy available, so ఇవన్నీ మీరు సెల్ఫ్ స్టడీ చేసుకోండి. So there is no time to discuss each and everything. So the Pelton wheel turbine. So what are the main components of the Pelton wheel? The main component is nozzle and flow regulating arrangement, runner and the buckets, casing, and a braking jet. These are the main components of Pelton wheel. So దీని గురించి డీటెయిల్ గా you can see this slide. Nozzle, the runner, casing, and a braking jet, right? Now if you see the velocity triangles, so ప్రతి turbine you are having a vane. So based upon the vane, you have to create the inlet triangles and the outlet triangles. So దీని గురించి ఆల్రెడీ మనం క్లాస్ లో డిస్కస్ చేసాము, మీరు ప్రాబ్లమ్స్ కూడా చేశారు, రన్నింగ్ నోట్స్, రైట్? So here the jet of the water from the nozzle, so the jet of the water from the nozzle strikes the bucket at the splitter. So see here, so this is a top view direction of the bucket, so which splits up into the two parts, splits into the two parts. These parts of the jet glides over the inner surface and comes out as the outer edge. Therefore, if we draw a outer velocity triangle, so మనకి వాటర్ అనేది ఇలా వచ్చి స్ట్రైక్ అయ్యి ఇలా బయటకు వెళ్ళిపోతుంది, this side or this side, right? So we can take one side triangle. Here it is a horizontal type, but here you are having a jet stripe because of this curvature. Now let H is a net head acting on the Pelton wheel, that is Hg minus Hf, where H is equal to cross head, Hf is equal to 4f Lv square by d square 2g, where d is equal to diameter of the penstock and d is equal to diameter of the wheel, small d diameter of jet, n is equal to speed. Now velocity of the jet inlet is root 2gh. Now u is equals to u1 minus u2. See here, so it already been class lo vesaru, okasari keep your running notes beside so that it will be easy for you. Okay, now see here at the center point ABC, so here the v1, here it is v2, so here it is u1, here it is u2, vr1, vr1, here we are having vw2, vw1, vw2. So like this you are having, first you have to draw the velocity triangles, right? So the velocity triangle at the inlet will be the straight line where vr2 is equals to v1 minus u1, that is v1 minus u. Next, vw1 is equals to v1, Therefore, alpha is equal to 0, theta is equal to 0 degrees. For the velocity at the outlet, VR2 is equals to VR1 and VR2 is equals to VR2 cos pi. Therefore, the force exerted Fx is equal to rho into A V1 Pw1 plus Vw2. Okay. Now, as angle beta is acute angle in the figure, see here, as angle beta is acute angle, it is positive sign. Also in this case, series of vanes, the mass of the water striking rho A1 and not rho A2, rho A V2. In this equation 1, A is the area of the jet pi d square by 4. Now the net work done is equals to Fx into U. So upon solving this one, we are getting the power given to the runner of the jet. So therefore, the work done per unit of water striking the jet, this one is a striking the jet. So upon solving this one, we are getting this one. Now the energy supplied to the jet inlet is in the form of kinetic energy. Therefore, the kinetic energy per second is equals to half m v square. So m is equal to rho into a into v1 v square, that is v1 square. Now the hydraulic efficiency is work done by kinetic energy of the jet per second. So work done రాయండి ke ఈ ఫార్ములా కింద అప్లై చేయండి. Therefore, so upon solving this one, this is a 4. So ఇవన్నీ solve చేసుకుంటూ వెళ్తే, so finally we are getting the values, substituting values. This one 5. And later the efficiency will be given as, so finally the efficiency is this one, right? Efficiency of hydraulic efficiency is this one for the Pelton wheel. So this derivation we have already discussed in the classroom notes, right? So based upon this derivation formulas, we are having some problems to discuss. So the problems kuda ekku nenu cheppanu, already have written some of the problems, many problems in your notes. So practice those problems, right? So I will give the important questions at the end of this total topics, so that I will practice and mid to I can help you, but in the external exams you have to practice on your own, and that purely depends upon not luck, that purely depends upon your practice. Okay. Now the Pelton wheel, see the Pelton wheel is a mean bucket speed 10 meters per second and rate is 700 liters per second, head is 30 meters. The deflection is bucket. So every time I'm saying you read the question 2 or 3 times, write the minimum given data, right? So the figure, the formula to find what you minimum మీరు రాసారంటే you will get minimum 4 or 5 marks for every question in the external question paper. So that ప్రతి క్వశ్చన్ కి minimum 4 marks వస్తే ఈజీలీ మీరు ఆన్సర్ రాకపోయినా calculations చేయకపోయినా easily you will get 15 to 18 marks only by writing this given data and the figures. And the balance of 10-15 marks మీరు థియరీ రాసారంటే ఈజీలీ 30 ప్లస్ మీరు స్కోర్ చేయగలుగుతారు, రైట్? By this figure, so draw the figure and draw the triangle. So ఇవన్నీ as it is మీరు వేయండి. So please practice this problem, this figure for this Pelton wheel, right? Now the given data, speed of the bucket u is equal to u1 minus u2, that is equal to 10 meters per second. Now the discharge is 700 liters per second, that is 7.7. Head of the water is 30 meters. Angle of deflection in the 160 degrees. Therefore, the angle of deflection is 160, means pi is equals to 180 minus 60, that is 20 degrees. Therefore, the coefficient of velocity CV is equals to 0.8. Now, the velocity of jet V1 is equals to CV into root 2GH. So upon solving, you are getting this one. Now, VR1 derivation ఎలా చేస్తున్నామో ఇక్కడ కూడా అలానే చేయండి. VR1 is equals to V1 minus U1. So ఎలా వచ్చింది? See here, see the figure VR1 is equals to V1 minus U1. అంతే కదా? VR1 is equals to V1 or VW1 minus U1. So figure వేస్తేనే this centrifuge, this unit file of for every problem minimum you have to draw the figure, then only you will get the formulas. Or మీకు idea ఉంటే directly you can draw the do the calculations without figure also. Now, upon solving, we got the value of V1 is equal to 23.7. Now taking from the outlet velocity triangle, VR2 is equals to VR1, that is divided by S. VWT is equals to VR2 cos pi minus U2. This is the answer. Now work done per jet per second is equals to rho into A into V1 into VW1 plus VW2 into U. So finally the work done is this one. Now the power is divided by 1000, the power is 186. Therefore the hydraulic efficiency formula వచ్చేసి ఇది hydraulic efficiency 2 of VW1 plus VW2 into U by V1 square. So finally you are getting the efficiency is 94.54. So ఇలాంటి ప్రాబ్లమ్స్ ఆల్రెడీ మీరు ప్రాక్టీస్ చేశారు, తర్వాత కూడా ప్రాక్టీస్ చేయండి. Next, coming to the second problem. A Pelton wheel is designed for the following specifications. So this is a given data to find what the wheel diameter, the number of jets required, and the diameter of the jet. First at the given data, you will get minimum 2 marks, right? So not in the mid questions lo kaadu, external paper lo given data మీరు నీట్గా రాసి ఫిగర్ నీట్గా ఎక్స్ప్లెయిన్ చేసి టు ఫైండ్ అండ్ వాట్ టు ఫైండ్ ఆర్ డిటర్మైన్ ఆర్ మినిమం చేసుకుంటూ 2-3 ఫార్ములాస్ వేశారంటే డెఫినెట్లీ యూ విల్ గెట్ ద మార్క్స్. Next, given data is SP is equals to this one, head is equals to this one, N is equals to this one. Now overall efficiency is 86%, 0.86. Now the ratio of jet to the diameter is T by D, that is equal to 1/6. Now the coefficient of velocity KV1 or CV is equal to this one. Now KU1 is equal to 0.45. Velocity of jet is equals to V1 is equals to CV into root 2GH. The value is this one. The velocity of a wheel U is equals to U1 minus U2. The speed ratio is equals to velocity of wheel is equal to speed ratio into root 2GH. So upon solving this one, we are getting the diameter is 0.989 meter. But we know that D by D is 0.1/6. So upon solving this one, discharge of one jet. So keeping the values, so the efficiency, overall efficiency is SP by WP, that is this one. Therefore keep on solving this one, we are getting the total discharge Q is equals to 3.672. How many number of jets? The number of jets is equals to total discharge by discharge of one jet. Therefore 3.6 divided by discharge of one jet is 1.8, that is a number of jets are 2. So like this you have to solve the problem whenever you are getting any type of turbines. Next one is how to design. So if you get a 2 marks question, design a Pelton wheel means. So the design of Pelton wheels, the data is first to determine the diameter of the jet, determine the diameter of the wheel, determine the width of the buckets, which is 5 into D, depth of the buckets, that is 1.2 into D, number of buckets on the wheel, size of buckets means the width of the depth of the buckets. Next, a Pelton wheel is to be designed for the head. A Pelton wheel is to be designed for the head of 60 mm, 60 meters. Meters running at 200 rpm. So this is a power, so this is efficiency, velocity. So write the given data, write all the given data. What is the velocity of the jet? Velocity is equal to CV into root 2GH. Find the value, find the U1, you will get the values. Therefore find the diameter D. Now what is the second thing? Diameter of the jet, small d. The efficiency is given. Overall efficiency is equals to SP by WP, that is so and so. Finally, you are getting the discharge. Q is equals to A into velocity. Therefore, is a value. Finally, with this, we are getting the diameter D. Now, what is the size of the bucket? Width of the bucket is equal to 5 into D, and depth of the bucket is 1.2 into D. The number of buckets on the wheel is given by Z is equals to 15 plus D by 2D, which is equal to 24. Next. Determine the power given by the single jet of runner of Pelton wheel, which has a tangential velocity at 20 meters per second. So the same problem, similar problems. మీరు పర్సనల్గా మీరు చెక్ చేసుకోండి. The time is up. Okay. So if you have any doubts, just you can unlock your mic and you can talk to me. Next one is reaction flow turbine, right? Radial flow reaction turbine. So see here how the process is going on. Water from the penstock is going in this direction, is rotating in this direction, going into this runner and expelling from this center side. So this is the shaft of this runner. Okay, next. In a radial flow turbines, the water flows in radial direction. By the name itself, it is saying that in a radial flow turbine, the water flowing in a radial direction. The water may flow radially from outwards to inwards. So ఇవన్నీ మీరు పర్సనల్గా చదువుకోండి. It will be, this is a self study so that you can easily understand what's happening. Okay. If the water from the outwards to inwards through the runner, if the water flows from outwards to the inwards through the runner, the turbine is known as inverse radial flow turbine. And if the water is flowing from inwards to outwards, the flow is outwards radial flow. So లోపల నుంచి బయటికి వెళ్తుంటే దాన్ని ఏమంటాము? అవుట్వర్డ్ అంటాము. Outside నుంచి inwards కి వస్తుంటే, that is we are calling them as inverse reaction turbine. Simply, the reaction turbine means that the water in the inlet of the turbine possesses kinetic energy as well as a pressure energy. As the water flows through the runner, the part of the pressure energy goes on charging the kinetic energy. Thus, the water through the runner is under the pressure. The runner is completely enclosed in an airtight casing of the runner. It is always full of water. Then what are the main components of the reaction turbine? Casing, guide mechanism, runner, and the draft tube. So casing అనేది యూనిట్ 5లో కేసింగ్ అన్నిటికీ ఒకటే మీరు రాయొచ్చు. వాట్ ఆల్ యూ గెట్ ఎనీ టైప్ ఆఫ్ కప్లాన్ టర్బైన్, పెల్టన్ టర్బైన్. సో కేసింగ్ గురించి ఏమైనా రాయాలనుకున్నప్పుడు యూ కెన్ రైట్ ఆల్ ఎనీ సేమ్ మ్యాటర్ ఫర్ ఆల్ ద టర్బైన్స్, రైట్? నెక్స్ట్, గైడ్ మెకానిజం. సో ఇవన్నీ మీరు సెల్ఫ్గా చదవండి. దేర్ ఇస్ నో టైమ్. రన్నర్, నెక్స్ట్ draft tube, next inward radial flow turbine, next coming to the velocity triangles and the work done by the water on the runner. So for this Francis turbine, the velocity triangles from the work done by the runner, the work done per second. So this is the value, right? So ఇవన్నీ మనం చేసాము క్లాస్ నోట్స్ లో. జస్ట్ recall it. So VW1, V1, U1, U2, diameter T1, N, right? Next, work done this one. So finally, so this is a figure of this Francis turbine. See all these cases, hydraulic efficiency, RP by WP. Next. So the discharge is radial outlet where V2 is equals to 0. Efficiency is equals to VW1 U1 by G into H. Coming to the definitions, what is the speed ratio? The speed ratio is equals to u1 by root 2gh. The speed ratio is defined as u1 by root 2gh, where u1 is equal to tangential velocity. The flow ratio, this one, right? Next, discharge of the tube. Discharge of the tube. The discharge of the tube through the radial flow direction is q is equals to pi d1 b1 into v f2. That is equals to pi d2 b2 into v f2. So these are the notations for that. So the head is, it is given by head is equals to p1 by rho g plus v1 square by 2g. That is, head is equals to potential energy plus kinetic energy. Okay. Next, coming to the radial discharge. So the formula is h is equals to h minus v square by 2g is equals to 1 by g vw1 u1 plus or minus vw2 u2. Next. So coming to the problem, a reaction turbine works at 450 rpm and a head of 120 rpm. The diameter of the inlet is 120 centimeters. The flow area is 0.4 meters square. The velocities are 20 degrees and 60 degrees. Determine the velocity, flow rate, and the power developed. Right? So write the given data. So manaki ikkada ee turbine ku vachesi, because of this reaction turbine, so manaki vane vachesi ee rakanga untundi. Initial cases lo the vane is like this. Mana indak cheppuna Pelton Wheel. So that's why horizontal ga ila vachi ila vellipoyindi. But in case of this turbine, the vanes are V shape. V shape lo undi kabatti ikkada oka triangle vastundi, inlet triangle, outlet triangle. So inlet triangle, outlet triangle ekkada vastayi? Only in the reaction turbine, right? So for this Pelton wheel, we are getting one inlet triangle is straight and outlet triangle is outlet is, it's a triangle shape, right? So the values is given. So this is the final answer, 85.85. 85.85 is the power developed. So we'll discuss the time is up. We'll discuss the other lecture in the other lecture. So we'll stop here. I will continue this lecture in the other session. So we are having a Francis turbine, another turbine also, right? So I will provide the timing